So the broadest categories of solids are crystalline solids and amorphous solids. And amorphous solids are disorderly. It's just kind of a mess of molecules or atoms. While crystalline solids have an orderly arrangement called a lattice. Now here obviously it's two-dimensional, but the lattice is in three dimensions. And it's made up of these identical unit cells that keep on repeating in every direction in the lattice. So if you took the lattice of a solid and looked at any 3x3 square, they would basically all look the same. And so we can classify solids based on what type of substance is at these lattice points. What makes up the lattice. So ionic solids have ions at the lattice points. For example, in NaCl, the lattice would consist of alternating sodium plus ions and chlorine ions. In a molecular solid, at each lattice point there is an individual molecule. For example, in ice, at each of these points we would have an individual water molecule, and of course they would all be held together by the intermolecular forces. The last type is an atomic solid, and in an atomic solid each of these lattice points is occupied by an individual atom. And there are further three more categories within atomic solids. Metallic solids have metal atoms at the lattice points, and they're held together by what's called delocalized covalent bonding. The delocalized means that the electrons can move about. The valence electrons are free to move. And this bonding is also non-directional, which basically means that the atoms in the bond do not have a preference as to what position they are relevant to the other atoms in the bond. Another type of atomic solid is network solids. Now these have strong directional covalent bonds, as opposed to the non-directional bonds in metals. So network solids form huge molecules. So you can't really see a distinct individual molecule within a network solid. It's just a big chain of atoms that doesn't have a beginning or end. Now group 8A solids involve the noble gas atoms that are held together by London dispersion forces. Because remember, the noble gas atoms don't usually make bonds with other atoms. So now we're going to look at the properties of each of these kinds of solids. So first we start with metals. Now the simplest model of a metal is the electron C model, in which we have an array of these metal cations, and their valence electrons are floating around in this kind of sea of electrons. So the covalent bonding in metals is strong, which is why metals are tough and have high melting points. And again, the bonding is also non-directional, which means that they don't have a preference as to what shape or position they're in. So this basically allows metal cations to slide around, which makes metals malleable. You can pound it into a sheet, and ductile, which means you can make it into a wire. And these delocalized moving electrons is the reason for why metals can conduct heat and electricity well. So alloys are substances with metallic properties that consist of a mixture of elements instead of just one metal. And there are two basic ways to make an alloy. In an interstitial alloy, some of the spaces between the metal cations are filled with smaller atoms. And in a substitutional alloy, some of the metal cations are just replaced by other metal atoms with a similar size. So next we have network solids, which again are just huge molecules instead of individual molecules. So here's a network solid. You can see each of these atoms is a carbon and is just bonded together in a huge jumble. And because it's just one giant molecule, all of these are covalent bonds, not the weaker intermolecular forces. So network solids usually have very high melting points because in order to melt this, you have to break the covalent bonds instead of intermolecular forces. And network solids are also usually insulators because they don't have the free valence electrons that metals do. The two most common atoms that form network solids are carbon and silicon. Carbon forms diamond and graphite, which are just both pure carbon, and silicon can combine with oxygen to form huge silica molecules. And again, since it's a huge molecule, the formula for silica, SiO2, does not mean there are individual molecules with one silicon atom and two oxygen atoms. It just means in this huge molecule, this mess of silica, for every silicon atom in the chain, we have two oxygen atoms that correspond with it. Molecular solids are insulators, soft, and have low melting points. Because unlike network solids, molecular solids have individual molecules, not just a huge chain. So these molecules have to be held together by those weaker intermolecular forces, such as London dispersion or dipole-dipole, depending on the molecule. So of course, these are much weaker than covalent bonds. So when you melt a substance, all you have to do is break the intermolecular forces instead of the covalent bonds within the molecules, which is why molecular solids have the low melting points. The last type is ionic solids, which are insulators in the solid form, but when you dissolve them into the ions, that's when they conduct electricity. They are also hard and have high melting points because the ions in the lattice are held together by very strong electrostatic forces between the oppositely charged ions. So the bonds are very strong, which causes the high melting points.